All right, diving in today, and I think we've got a really fascinating one. We're going to be talking about Hermann Weyl.
Oh, a giant. A huge figure.
Absolutely spans so many different areas: math, physics, philosophy.
Really, I mean, this is the kind of guy you wish you could just have a conversation with for like hours and hours. Just pick his brain.
Absolutely. So for our listeners, you're out there really trying to grasp the big questions. What is knowledge? What is reality? We're going to look at Weyl through that lens, that philosophical lens.
And what's really striking, I think, for someone interested in philosophy is that with Weil, it wasn't like philosophy was some separate thing he did on the side. It was really baked into his thinking from the start. You see it in his work on the foundations of mathematics and his approach to relativity. It's all connected. And I mean, that period between 1917 and 1924, wow, that's when he published Space-Time, Matter, and Dust Continuum. Talk about a burst of intellectual energy.
Yeah, that's actually kind of what we're going to be digging into today.
Right.
Sort of like, what are some of the core philosophical ideas that are running through Weyl's work? His perspective on the ego and the external world. Like, how do we know stuff? What is mathematical knowledge, physical knowledge? And, I think it's important to see how his views on these things evolved over time.
Right. So where do we start? I think it's got to be with his metaphysics. Weil has this central concept of the ego as primary. It's the starting point. The ego is the one that has this direct access to what he called the given, basically the raw data of experience. In his own words, the world exists only as met with by an ego. And I mean, that's 1934 Weil. So for philosophers, this raises all sorts of questions. Like, okay, is he flirting with solipsism here?
Yeah, for sure,
Yeah.
right? It's very much like the ego is at the center of the universe,
Oh,
so to
yeah.
speak. So how do we move beyond just this one, individual consciousness?
Yeah.
If that's our starting point, how do we get to like a shared world?
Yeah, great question. So Whale says that the ego, through self-reflection, comes to recognize its own function. It sees itself as and I'm quoting here, a conscious existing carrier of the world of phenomena. So the ego understands itself as this kind of like subject that experiences the world. But here's where it gets really interesting. Whale then says that through analogy and empathy, the ego conceives of the thou, like another ego. So it's not just me in my own little world. I can like grasp the existence of other centers of consciousness.
I see. So there's this kind of bridge, right, between consciousnesses.
Yeah.
Like, I recognize that you were also a subject experiencing the world. Okay.
Exactly. And Whale emphasized this shared like luminosity between the ego and the thou, this mutual recognition of being conscious subjects. It's pretty profound when you think about it, trying to ground intersubjectivity in something really basic about experience.
Yeah, absolutely. But then what about everything else? Everything that's not a conscious subject? Like, what about the objective world? The stuff that science tries to describe. How does that fit in for Weyl?
Yeah, okay, so that relationship is different. It's not like the relationship between the ego and the Tao. He says the objective world is this radically other thing. It's opaque, it's transcendent, almost like, I don't know, I'm thinking of Kant's noumenal realm, this thing that's outside of our direct experience. So for Whale, the ego doesn't directly perceive this objective world. Its existence comes from a kind of like postulation, like an act of faith almost.
So it's not something we can know for sure in the same way that we know our own consciousness.
Right, exactly. It's more like we need to posit it to make sense of our experiences, but it's not directly given.
I see. Okay, that makes sense. And this idea that, we can't directly grasp the objective world, it makes me think about, quantum theory, how quantum physics describes a world that's really bizarre and doesn't fit with our everyday intuition.
Yeah, absolutely. Like, think about it. Many physicists say that the quantum world can only be understood through really abstract mathematics. You can't picture it in your mind like you can picture, a ball rolling down a hill. And that fits perfectly with Weyl's idea that objective reality is something we have to construct through these like symbolic representations.
Yeah. That's a cool connection. Okay, so we've got this triad, right? The ego, the thou, and the objective world. Is that the whole story for a while?
Well, not quite. In his later work, he actually started thinking about adding a fourth element, a godhead that lives in impenetrable silence, as he put it. It was, I think, partly inspired by his reading of the mystic Meister Eckhart. It was an attempt to create this, like, symmetry between the subjective and the objective. But I mean, this was kind of a late-stage idea, and he never really fully developed it.
Fascinating. It's always cool to see how thinkers are influenced by things outside their main field. Okay, so along with this deep dive into metaphysics, Weyl was also, really digging into the foundations of mathematics, which, as a philosopher, I find really interesting. Because, in math, you're always looking for that absolute certainty.
For sure. And during that same period, like the early 1920s, Weyl was really wrestling with the problem of the continuum. Like, how do you make sense of the real numbers in a rigorous way? And, he got pretty critical of the whole set theoretic approach, the stuff that Cantor and Dedekind had done. He called it, like, permeated by contradiction. Those are strong words for a mathematician.
Yeah, no kidding. So what was his issue with set theory, and what did he propose as an alternative?
Well, he was really concerned about what he called impredicativity, the idea that you could have a set that's defined in terms of a totality that includes itself. It's a bit mind-bending, but Weyl thought this kind of circularity was a recipe for trouble. So in his book, Das Continuum, he tried to develop a different approach. He called it a predicative formulation of math. He wanted to build everything up from the natural numbers, like 1, 2, 3, and so on. And he wanted to use only very basic logical operations. No fancy set theoretic stuff.
Okay, so it's like, back to basics. Start with the simplest things and build from there.
Yeah.
But didn't that, really limit what he could do in math?
It did. I mean, he knew that he couldn't prove certain key results from classical analysis. Like, for example, Dirichlet's principle, this idea that, you can always find the smallest number in a set of numbers that has an upper bound. But Weyl was willing to accept these limitations because he thought it was the only way to have a truly secure foundation for mathematics.
So he's prioritizing, logical rigor and avoiding contradictions over, being able to prove certain theorems. That's a pretty fundamental choice, right?
Absolutely. And his concerns also extended to the whole way we think about the continuum, like our intuitive understanding of it. He felt there was a huge disconnect between this intuitive notion of a continuous flow and the way mathematicians try to represent the continuum with these discrete points. It's like, how do you get from these individual points to the experience of something that's smoothly flowing?
Yeah, it's kind of like those Zeno's paradoxes, right? Like trying to divide motion into an infinite number of static points. It's
Yeah.
like our experience just doesn't work that way.
Exactly. And Weyl was really sensitive to that. He actually used that phrase continuous flow to describe our experience of time. He said that this experience of time is primitive, like we can't really break it down into smaller pieces. And he thought it was really hard, if not impossible, to capture this experience using the language of points and sets. For him, the mathematical concept of a real number, even though it's very precise, is still ultimately separate from our lived experience of continuity.
Yeah, and that makes total sense. We talk about, points in time, but our experience is always of this flowing present.
Exactly. So for Weyl, the mathematical tools, while useful, don't quite capture the full richness of our experience. And this is where his interest in Brouwer's intuitionism comes in. This is a philosophy of math that really emphasized mental constructions. We create math, it's not some pre-existing thing out there.
Right. So it's not about discovering some eternal truth. It's about constructing mathematical objects and systems. That's a pretty big difference from a Platonic view of math.
Huge difference. And Weyl was totally on board with the intuitionist program. He saw existential statements in math like there exists a number with such and such a property, not as claims about an independent reality, but as what he called judgment abstracts. Think of a treasure map. It tells you there's treasure, but it doesn't tell you exactly where it is. You still have to go out and find it. That's kind of how he saw these existential statements. They give you a direction, but they don't tell you the whole story.
Okay, that's an interesting analogy. So the map doesn't guarantee you'll find the treasure. It's just a guide. And what about universal statements? Like all even numbers are divisible by 2.
Yeah, so those are a little bit different. Weyl called them judgment instructions. They're like recipes. They tell you how to do something, like how to construct an even number. But even those, for him, weren't about some pre-existing mathematical reality. They were about our own constructive abilities. And even though intuitionism has its own challenges, Weyl really believed that it was the best way to capture this idea of math as a human creation, this idea that we're actually building the mathematical world.
Yeah, that makes sense. And of course, you can't really talk about Weyl and intuitionism without talking about Hilbert,
Right.
his mentor. He had
Yeah.
a very different view of math.
Oh, absolutely. That was one of the big intellectual clashes of the 20th century. Hilbert, he was all about solving problems. He was famously optimistic. We must know, we will know. He thought there were no limits to what math could achieve. Weyl, on the other hand, he was more cautious. He embraced the limitations that came with intuitionism. He thought that some things in math just might be beyond our grasp.
So you have Hilbert, who's almost like a Platonist, believing in this pre-existing mathematical realm. And then you have Weyl, who's more grounded in human experience and our constructive abilities. It's kind of like Kant versus Plato in a way.
Yeah, I like that analogy. And Weyl actually had a really neat way of summarizing the three main positions. Set theory, he said, was like naive realism, just assuming that sets exist out there in the world. Brouwer, he said, was an idealist because he emphasized the role of the mind in constructing math. And Hilbert, he said, was trying to jump over his own shadow, like trying to represent this transcendent realm of mathematical truth through formal systems.
Jump over his own shadow, that's a great image. So Weyl saw the limitations of formalism, but then, he also did a lot of work in physics. And physics is all about describing the real world. So how did he reconcile his intuitionist leanings with the needs of physics?
Yeah, that's a really important point. So while Weyl thought that pure math should stick to what we can intuitively grasp, he also recognized that physics has to go beyond that. Like, you can't just intuit your way to the laws of physics. You need experiments, you need observations, and you need math to make sense of it all. So he was willing to use more powerful mathematical tools, even if they weren't strictly intuitionistic when it came to physics.
So it's like a kind of pragmatism, right? Like you use the best tools for the job, even if they don't fit perfectly with your philosophical ideals.
Exactly. And later in life, he actually became more interested in axiomatic systems. Kind of going back to some of the stuff that predated Hilbert, he seemed to be moving towards a more blended approach, where you have both axiomatic and constructive methods working together.
Okay, that's really interesting. So it's not an either. It's more like, let's use all the tools we have to understand the world. All right, so let's shift gears a bit and talk about Weyl's contributions to physics, because they're obviously huge, and I think they have a lot of philosophical implications as well,
Yeah.
especially when it comes to the nature of space and time and the fundamental forces of nature.
Absolutely. I mean, just think about his work on generalizing Levi Civita's concept of parallel transport. Weyl developed this thing called an affine connection. It's a way of describing how vectors change as you move them around in a curved space. And the really cool thing is that he did it without having to embed the space in a higher dimensional space. It's like the geometry is intrinsic to the space itself.
Okay, that sounds pretty abstract. What's the philosophical significance of that?
Well, it suggests that there's a fundamental geometric structure to space-time. It's not just something we impose on the world, it's already there. And it exists independently of how we choose to measure distances and intervals. It's a deep statement about the nature of reality.
I see. So it's not about, using some external ruler to measure space.
No.
The geometry is built into the fabric of space-time itself. Okay, that's pretty mind-blowing. And how did this connect to Einstein's general relativity?
Yeah, so Weyl showed that you could define a coordinate system called a geodesic coordinate system, where the components of a vector stay the same when you move it a tiny bit. And this connects to the idea in general relativity that you can always make gravity disappear locally. Like, if you zoom in on a small enough region of space-time, it looks flat. And Weyl saw this local flatness as a key feature of his affine connection.
Okay, so there's this interplay between the local and the global. Like locally, space-time can look flat, but globally, it's curved. And Weyl's math is capturing that.
Exactly. And Weyl argued that it was the affine connection, not the metric tensor, that really mattered for physics. Like, the metric tensor tells you how to measure distances, but the affine connection tells you how things change as they move through spacetime. And that's what you need to formulate the laws of physics as differential equations, whether it's Newtonian physics or general relativity.
So it's like the way things change is more fundamental than the static measurements of distance. That's a really cool shift in perspective.
Totally. And then Weyl took this even further and developed these things called differential projective geometries, or geometries of paths. These focus on the paths that particles trace out in space-time, rather than on how we parameterize those paths. And he connected this idea to his concept of the guiding field, which was his way of combining gravity and inertia into one unified concept.
And this all led to his attempt to create a unified field theory, right? Like to bring gravity and electromagnetism together under one geometric umbrella.
Yes. In 1918, he proposed this theory based on what he called a purely infinitesimal metric geometry. We call it Weyl geometry now. And his big idea was to use this thing called gauge invariance to unify these forces. He saw that the conformal structure of space-time, which basically determines how light cones behave, didn't uniquely determine the geometry. There was some freedom, some wiggle room, so to speak. And he thought that maybe that freedom could be used to accommodate electromagnetism.
Okay, so he's seeing this deep connection between geometry and the fundamental forces. That's a pretty ambitious and philosophically rich idea.
Totally. And Weyl was also critical of Riemannian geometry, which is what Einstein used for general relativity. He thought it was too focused on measuring lengths at a distance. He wanted a geometry that was more local, more focused on infinitesimal changes. So he came up with this idea of conformal structure, which preserves angles and light cones but allows for changes in scale. And then he added this length connection or gauge field to it to create Weyl geometry.
Okay, and I know this led to a problem, right? This famous second clock effect.
Yeah, in Weyl geometry, if you have two clocks that start at the same point and travel along different paths, they can end up ticking at different rates, even if they return to the same point. And that's because the notion of distance itself becomes path dependent. Einstein was like, nope, that can't be right, because we know that atomic clocks are super precise and their rate doesn't depend on their history. So that was a major challenge for Weyl's theory.
So experiment contradicted his theory. How did he respond to that?
Well, at first, he tried to say that maybe there's some unknown physics going on at a really small scale that we can't see yet, and that this physics would explain why we don't see this second clock effect in the real world. But, other physicists, like Pauli, weren't convinced. They thought it was kind of a cop-out. So later on, Weyl changed his tune. He said that maybe his geometry wasn't meant to be a literal description of the world. Maybe it was more like a formal analogy, like the connection between electromagnetism and the metric field was more mathematical than physical.
Okay, so he kind of backed off from the strong claim that his geometry was like the true geometry of the universe. And this connects to that broader philosophical debate about conventionalism, right? Like, to what extent is geometry just a convention we impose on the world?
Absolutely. Weyl was definitely not a conventionalist. He believed that the metric field was a real physical field, just like the electromagnetic field. And he wanted to find a way to derive it from more basic principles. So he came up with this method called the causal inertial method.
And what was that all about?
Well, he wanted to start with just the most basic things we can observe in spacetime: events, the paths of particles, and the paths of light rays. And from those, he wanted to build up the whole geometric structure. First, you get the differential structure, then the conformal structure, and finally, the full metric tensor.
So it's like starting from scratch, from the most fundamental observables, and trying to construct the geometry from there. That's pretty ambitious and philosophically interesting because it's about grounding geometry in something more than just abstract mathematical ideas.
Exactly. But of course, there have been criticisms of this approach. Some philosophers of science have argued that it's circular, like you're already assuming certain things about the nature of particles and their motion in order to derive the metric. So it's a bit of a tricky issue.
It seems like Weyl was always walking this tightrope between like the elegance of math and the constraints of the real world.
Totally. And that tension is also there in his work on the laws of motion. He had this really interesting critique of Einstein's interpretation of Mach's principle, which is the idea that inertia is caused by the distribution of matter in the universe.
Okay, so Weyl is taking issue with one of Einstein's core ideas. What was his problem with it?
Well, he thought that Einstein's version of Mach's principle wasn't really consistent with general relativity. Like, general relativity is a local theory, but Mach's principle is about the global distribution of matter. So Weyl came up with this alternative idea of an inertial structure field, which he thought was more compatible with the spirit of general relativity.
So instead of saying that inertia comes from the distant stars, he's saying it comes from this field that permeates all of spacetime.
Exactly. And he called this view a field-body relationist ontology because it emphasized the importance of both fields and matter. They both have a real existence and they interact with each other. And he even had this famous example of like a piece of plasticine in a completely empty universe. He argued that even in that case, there would still be a resistance to acceleration because of this inherent inertial structure field.
So inertia isn't just about the presence of other matter. It's a fundamental property of spacetime itself. That's a pretty radical idea.
Right.
And what about Weyl's views on matter itself? Like, what are particles made of?
Yeah, so he actually went through a bit of an evolution on that question. Early on, he was sympathetic to this idea called the pure field theory of matter, which basically tried to say that particles are just like knots or concentrations of energy in the field. But later on, he moved away from that view, partly because of the development of quantum mechanics, which introduced this whole new way of thinking about matter and fields. So he came up with this alternative called the agents theory of matter.
Okay, and what was the difference?
Well, in the agents theory, matter and fields are both fundamental. They both exist and they interact with each other. It's not like one is more real than the other. And he did some really cool work on trying to understand the mass of charged particles. And he even had this early idea about like one-dimensional tubes in space-time, which are kind of like a precursor to wormholes.
So he's really like pushing the boundaries of what we think is possible in physics. And then, of course, he also made some important contributions to cosmology,
Right.
like the study of the universe as a whole.
For sure. He had this postulate called Weyl's postulate about how galaxies move in a homogeneous and isotropic universe. And he actually derived an early version of Hubble's law, which relates the redshift of galaxies to their distance. And he did this before Hubble himself made the observational discovery.
Wow, so he's really ahead of his time.
Yeah.
And what about his views on the nature of general relativity? Like, was it a global theory or a local theory?
He was really adamant that it was a local theory. He don't think you needed to assume anything about the global structure of the universe to make general relativity work. He was critical of Einstein's static universe model, and he explored some of the alternative models, like de Sitter's expanding universe. He was really open to the idea of a dynamic cosmos.
Okay, so he's embracing the idea that the universe is not static, it's changing and evolving. And we haven't even talked about his work on group theory, which is another huge area where he made major contributions.
I know, it's amazing how much he did. And his work on group theory was actually motivated, at least in part, by his philosophical thinking about relativity. He was trying to understand the mathematical structure of the theory, and he saw that groups played a really important role. And he also had some interesting philosophical critiques of other approaches to geometry, like Cartan's work.
Okay, so we're seeing this constant interplay between math, physics, and philosophy in Weyl's work. It's all interconnected. And I guess we should wrap up by talking about his views on quantum mechanics, because that was the other big revolution in physics that happened during his lifetime.
Yeah, and Weyl's engagement with quantum mechanics was really fascinating. He was clearly drawn to the mathematical power of the theory, but he was also struggling with the philosophical implications. Like, what did it mean for our understanding of reality?
So he was both excited by the possibilities and troubled by some of the consequences.
Exactly. And his own background in philosophy, especially his interest in symbolic construction, probably helped him accept some of the weirder aspects of quantum mechanics, like the fact that it's probabilistic and non-local. And he had some really interesting things to say about the measurement problem and the limitations of classical logic.
Yeah, and I remember that quote of his where he says that the objective world simply is, but our experience of it is fleeting and subjective. That really captures the essence of his view, I think.
It does, and Amail was really one of the first physicists to take the philosophical implications of quantum mechanics seriously. He wasn't afraid to ask the tough questions, and he didn't shy away from the fact that the answers might be really strange and unsettling.
Yeah, and I think his willingness to wrestle with those questions is one of the things that makes his work so enduringly relevant. He's not just giving us answers, he's showing us how to ask the right questions.
Absolutely. And he's reminding us that the search for understanding is a journey, not a destination, and that sometimes the most profound insights come from embracing the mystery and the unknown.
That's a great note to end on. Weyl's work is a testament to the power of human curiosity and the enduring quest to understand the universe and our place in it. So for our listeners, I would just encourage you to explore Weyl's work for yourselves. It's challenging, but it's also incredibly rewarding. And I think you'll find that his insights into the nature of math, physics, and reality are just as relevant today as they were a century ago.